Do you want to give it a few more minutes to see if people show up, or do you want to start?
No, that's fine. Huh? Huh? What type of paper is this? What's this called? It's just called green bar or blue bar. It's source code paper, so when you drop it, it doesn't fall into a million pieces. You can also lay it flat on the floor and cry if your program's not working.
I had a friend show me this kind of paper for their first project in OS. Yeah. It was taller than me.
Yeah,
I was like, I'm scared of this class.
Yeah, yeah, nice. No, you can still buy the printers that are brand new. It's also economical too. A ribbon costs $7.
Looks pretty cool though.
It's great for source code stuff. I mean, it's not good for anything but text, but it's pretty awesome for that.
It also just looks very hackery.
Yeah, totally. I had one of these printers at home and one in the lab also. It's coming along. The projector's working. We don't have a panel yet, but at least.
Oh, well, hey, at least the projector works.
Yeah, at least it's alive.
Yeah, you know. Oh, the 4330's midterm is today. And so there might be some people that are a little burned out from that.
Yeah. Do you have any victim that you knew was coming that we could just see if they're lost or?
That's yeah, I'm gonna send an email to everyone that RSVP.
We can just have a small seat party.
Right, yeah, and everyone can go home with a pizza.
Maybe two.
Yeah, maybe two pizzas. 7, 8, 9, 10. Exactly one pizza per person.
Okay, wow.
If no one else shows up, then we can like rock, paper, scissors for them.
So to be the one person who lost every single round of rock, paper, scissors and then couldn't get the pizza.
Be like round robin, rock, paper, scissors. Yeah. It's a great idea.
Well, I could take a quiz while we wait. See expertise 0 to 10. 0 means you've never seen it. 10 means you're like a black belt at C.
Maybe 1 or 2.
Okay, that's fair. You?
I mean, you're fast.
I know, but a 4? It should be better than that by now. You? 0 to 10.
4?
A 4. Okay.
I think 0.
0. Okay.
3 or 4.
3 or 4. I think you're all being shy now. What about you?
I don't know what's like how closely related it is to C++.
Yeah, I mean, quite more primitive, I would say. You're an expert C++ programmer?
Not expert, maybe. I think it was 2 years ago.
Okay, but you've seen it before and done some stuff, yeah. What about you? 0 to 10. C knowledge. Yeah.
Oh, 0.
0.
I don't know Java.
Huh?
I don't know Java.
Okay.
Ooh,
nice.
A convert.
All right. I'd say that's a good mixture, but it isn't because it's all 0 to 4.
Well, you know, if there were 10s in here, then what are they doing here?
Yeah, there
you know?
shouldn't be 10, so it would be crazy.
I've done most of my C learning the past like month or so taking 3501 and 3304.
Okay, it's cool.
So I'm like just starting to get into it.
Okay. Yeah. If anyone else shows up, I'll say this again, but I mean, basically, this starts with like hello world and goes into some really advanced stuff, so we can go as fast as you want, but like we don't want to go faster than you understand, because there's no point. And obviously there's no way in the time that we have to go through the whole stack, and that's not the intention, but the stack is intended to introduce you to a whole bunch of stuff, including like some stuff you would need to do, like interactive games, networking, all kinds of stuff. And so we'll get as far as we get, and then, you know, I would recommend that you just type in the rest, type in, compile, run, and just sort of follow along. So all the examples are heavily documented, so you can learn how to do like TCP, UDP, network programming, game stuff, pipes, inter-process communication, all kinds of remote controlling other programs, all kinds of stuff that's there. Yeah.
What would be like the pitch for learning C? Like what can you do with it that you can't do with other languages?
Everything important is written in C already. I mean, that's really the reason. And you need to know C for sure for writing any kind of operating system stuff, or device drivers and so forth. So I mean, you know, NVIDIA device drivers are written in C. Windows is written in C, Mac's written in C, the Python compilers and interpreters written in C, Java's written in C.
Will you able to do a path like this, but for C++?
No.
We do have one new instructor who is a C++ guru.
Yeah.
So we could do that.
Yeah, that's Hartmut Kaiser.
Kaiser,
Yeah, he's.
I don't know why I couldn't think of it.
He's the C++ expert. I don't use C++ at all, so I would be the wrong person.
I think we don't do it too much because the intro to CS for non-majors is the C++ class. So there's not that many classes in the major that focus on C++. C is just so useful.
Just that, yeah.
Yeah.
Yeah, if any systems programming. So yeah, all the infrastructure of the world is written in C. Even Go was written in C until they rewrote it in Go.
Oh, I didn't know
Yeah,
that.
so almost everything's C.
Wait, Go is written in Go?
It is now.
How does that work?
You have to write enough of a Go compiler, basically from scratch using assembler or whatever to get enough Go so that you can start writing the whole right. Yeah, basically it's continual bootstrapping. They deliberately wanted to distance themselves from C and like write the whole thing in Go. So it's pretty, huh?
Why?
Oh, just I mean, just it's a position. Their view is that basically you shouldn't be using C anymore, you should be using Go. The Rust people feel that way too, so which is fine, but I mean it's no time soon that C is disappearing.
It seems like a lot of the tech bros, like the cryptocurrency types, want C to become outdated.
Yeah.
But what did you say last time? It's like 15, Windows is 15 million.
Windows 50 million lines of C,
yeah.
Linux 50 million lines of C.
No one's ever
Mac
going to write
50
that.
million lines of C. I mean, it's not an overnight process. So even if you want it, even if you decided C sucks, I'm moving everything to something else, it takes decades for that to happen. So in the meantime, it's best not to be left behind. And writing high performance stuff in C is certainly not as easy as it's not as easy to program in as Java, and it can be very error prone if you're not careful and make silly mistakes. But the lack of seatbelts and stuff means you can do amazing stuff, and the performance is insane. So it's not quite as fast as assembler, but it's pretty close. And Java is substantially slower, and Python's, orders of magnitude slower, hundreds of times slower. Go is pretty fast. It's approaching C speed. Rust is a cool idea, but you find that it's, it is a cool idea, but you'll find that it's not really as easy to just switch to Rust as you would think, because the Rust compiler insists on all kinds of like proofs of correctness guarantees essentially, and so you can't just write any old thing you want in Rust because it just won't work, so it won't compile. So anyway, it's not a Rust.
All right, looks like we're gonna start rock, paper, scissors. And I think part of the like discussion about like slowness versus quickness of languages gets a little bit lost because Python is so widely used for like basic scripting, like running through a for loop 10 times.
And it doesn't matter.
Right, it seems like it just happens like that. It's like, okay, who cares if it took 0.01 milliseconds more? But when you get into things like, I don't know, like parsing databases or something where you're doing things in the orders of hundreds of thousands or millions of times, then those 0.1 milliseconds add up a lot.
Yeah, plus you can't write operating systems in Java or C or Python. It's not possible. So I think this projector is working better this time. I obviously can't see the screen. It's kind of a weird setup. I don't think it's.
I think this has wheels if you want to push forward a little bit.
Without really trashing.
Yeah, right.
It is nice to know what's up there. So, but anyway, if there's a blackout or something, you should tell me that you're not looking at anything. Which, yeah, now.
There we go.
Everyone have one of these? Okay.
Okay. And has everyone been able to log into the Alienware laptops if they're using them? It's this right here, and then which VM are
Use
they?
the Kali VM.
We're gonna use the Kali VM. Okay. Has everyone used a VM before, a virtual machine or virtual VMware? No. Okay. Cool.
You're on.
I'm on. Oh dear God. Okay. So if you're using the Alienware laptop, I see a few of y'all have your own laptops. If you're like well versed in VMware or just command line stuff, feel free to use your own laptop. But if you're a little bit more of a beginner, maybe like in the 0 to 3 range, I would really suggest you use the Alienware laptops. Just because everything's already done for you.
If you have a Mac and you have GCC, obviously it's fine to use a Mac.
Yeah.
But you need a command line and you need GCC.
Pretty much, yeah. Those are the two big things. Pretty much the only things. I guess like an editor.
If you can't, yeah, go ahead.
If we're like a 1 or 2 in C, but we've used a lot of Kali before and stuff as
as long as you have a command line, GCC, and then some kind of editor that
you need
like.
editor and GCC. That's it.
Yeah.
Yeah. But my whole thing will be in this terminal window. There's nothing else besides that.
So yeah, whichever machine you're on, if you're on the Alienware laptops, find the icon for VMware on your desktop. It's like 2 kind of squarish, rounded squares. And then use the, where is it? So it's like VM Kali-RE, right?
If you don't know what we're talking about, raise your hand and we'll come help you.
Yeah.
It'll quickly derail if you're not in the VM.
Right. Okay, yeah. You get one, I'll get the other.
Okay.
Okay, sweet.
Yeah, you file.
Okay, sweet. We're not to worry about.
And then go back to this.
Okay,
main
so
screen. Yes. Yeah. Exactly. Yeah, you follow that one. Yeah. And yeah, that's it. Do that and then start it. Yeah, there's some capture the flag VMs too. Don't use those. Use the Kali VM instead.
I don't know where I can use in Windows if I need to use something.
Oh, just VMware Workstation be here.
Oh, okay.
Yeah, there. And then do file open once you get there.
It's not much good for
Yeah, there. And go all the way back to the C drive, OSC, the one at the bottom. Yep, that one.
Yeah.
And then in virtual machines.
Just like scoot over to this station and then we'll work on there.
Yeah, Windows sucks, I know, but it's the way it is. And it's new Kali, it's that one. Double click on that and then choose that file. That's the config file. Oh no.
What did I do?
I don't know. Yeah, I undid it.
Okay,
So yeah,
Are you
choose
using
this one.
the secret sauce or
I'm
the?
trying to choose, but
Control C is undo.
okay.
Now just run that and you're good.
Yeah.
Yeah, do file, but it falls to its other.
Okay,
Go to the C drive all the way back.
you just click like that.
This PC, yeah. The
Oh, there we go.
version machines and the new column. Yeah, that one. Yeah, just open that one.
Okay, so yeah, click into here.
Yeah. Anyone still with that? You should see Einstein. If you don't, you're in the wrong VM. Root. It's root and 9 corner 9. These are the credentials you want this set.
Yeah, but okay, let's do that one.
Root and then 9 corner 9, all lowercase. With a K. Corner with a K.
There we go. Okay, perfect. All right, sweet. You're back. So, oh, this is this one. Oh my gosh.
Yeah.
This is one, I think the one from last week that was Daryl's from Daryl's class.
What happened?
She doesn't have either of the VMs.
Oh, they're not in C? They're not in the C right here?
Check and see.
They should be here. Yeah, so did he just like blow this away?
This was from like last year, and I think that they list all of them.
Yeah, it's
Oh, okay.
Just say I copied it. Yeah, and then root 9 corner 9 like that. And you should see Einstein, and then just open a terminal window and use whatever editor you want. If you don't know any editors at all, you can use like Nano, N-A-N-O. It's super easy to use. If you really want to graduate, you should use Emacs or Vim.
There we go. So it's so they're backwards. See the mouse is here, and I'm going to go this way, and it shows up there.
Oh, okay, backward. Got it.
Yeah, that's really exciting. And then... Oh, so it looks like you have like two of these open. Yeah, here we go. Not well. Get out of that guy. All right, and this is going to be, yeah, here, you can go ahead and type in the root 9 corner.
I think I can open mine.
Yeah. There you go. Okay, sweet. And you see 9 corner 9. Hit enter. And it's KO. No, all lowercase. Okay.
We're supposed to just see this guy's face.
Perfect. Awesome. You were there. You are ahead of the game. Very good.
Yeah. So I've been trying to make this swap from just like writing my code in VS Code on Windows to like actually using the Vim editor, but I find that debugging for me on Vim is like harder than on VS Code. How do I like find like bugs in Vim, or like what can help?
I mean, usually I just use GDB at the command line. The debugger GDB. GDB. That's the GNU debugger. It's the friend of GCC. It is the debugger for GCC. Yeah, and if you just go online and type GDB cheat sheet, you'll find something.
Okay. It just likes me.
Sorry you've joined the Vim.
There we go. All right, we're there.
Emacs, but it's all right.
Okay.
So I'm sorry you've joined the Vim squad instead of Emacs, but it's okay.
I mean, it's not too late. I've only been using it like a month or two.
No, once you learn one, you never change.
Yeah, so you're locked in for life.
Oh man.
No, you can never change.
Join the Vim army.
All right, so has everyone gotten into their Alienware machine or have their personal laptop set up? All good? All right.
Okay, all right, so let's just get going. So I want to accelerate as quickly as we can to get into some fun stuff. But again, you know, we're not here for me, we're here for you. I'd recommend, well, first of all, when you flip through the handout, when I talk about hello.c or something, you'll see ASCII art at the top, and the printout is broken with form feeds, so every program starts at the top of a new page. I've tried to document all of them as best I could. Hello.c is just a standard Hello World program, and I'm not doing it because that's like traditional or anything. I'm doing it because this is the program, maybe minus the printf hello, that you should always start with when you're starting from scratch. It's important enough that in Emacs, I'll just show you this. I mean, I have a macro that just starts with that, gives me that skeleton to start with. You may see old style C books that leave out the arguments for main and stuff and end up looking, something like that. Just get out of the habit of doing that, and write the skeleton. There's some reasons for doing that. In C, as you'll see throughout the night, these include files are necessary to get types and constants and function prototypes and stuff, basically all the functions and types that you want to use. The three most common ones are standard IO.h, which lets you do like reading from the keyboard and writing to the screen and reading files and so forth. Standard lib, which has like lots of memory allocation stuff and so forth. And then string.h, which is all the string functions for manipulating strings, concatenating strings, searching strings for characters and stuff like that. You're almost always going to need those three, and then you may need more. And so you'll learn which ones you need by just doing it, right? Of course, yeah, this is not supposed to be this slow. This Mac is slowly giving it up, which is sad. Linux, Unix-based systems, Macs and Linux, both of them have online man pages. And so if you don't know how to do something, you can just type man and whatever the thing is. And so like man printf, I just did like malloc, or man string copy. And so these are some of the functions you'll see later tonight, but the online man pages are awesome because you don't have to go onto the internet, end up potentially distracted, watching cat videos and stuff. Just stay in the command line and eliminate the cat videos and YouTube and stuff. You can edit in the command line, you can debug in the command line, you can get manual man pages in the command line, do everything here, and don't go outside of the box. At least give it a try. If you don't like it, then you can always do something else. So that hello is not very interesting because all it prints is hello. But yeah, it's a good place to start. So see that. All right. So the next one on the list, flip the page, is basic.c that just shows you some basic function calls and variable declarations and so forth. And so this is just meant to show you control structures and stuff like that. Everyone's done some programming. Like if anyone never programmed before,
It's okay if the answer is yes.
It's okay if the answer is yes, but it's going to be a little bit more painful because I expect that you've seen like control flow and loops and stuff like that. Otherwise, I'm not really sure how to proceed. So anyway, there's some functions declared at the top. And so functions declared in C have a return type, in this case, void, that just means it doesn't return anything, the name of the function, and then a list of arguments and their corresponding types. And so you see here that this function takes a whole bunch of arguments. It wants a character. A character is an 8-bit integer in C. It's not anything but that. It's a value between, let's see, either negative 128 to positive 127 or 0 to 255. It's an 8-bit, very tiny integer. And you can do arithmetic on it and stuff, as we'll see. Integers are bigger. On this particular machine I'm on and the machine you're on, integers are 4 bytes, which means roughly 0 to 4 billion. That's the range of them. Longs on the machines we're on, not necessarily on Windows, are 8 bytes, which means 0 to 4 billion squared. So it's a big integer. And then long on some platforms would be bigger, but on these it's still just 64 bits. So long and long are the same. On Windows, long is the same as an integer, and long is a long, but we're not going to get into all platforms of the differences there. Float and double are 2 different precisions of real numbers, floating point numbers. And then you have unsigned variants of all these. Unsigned int, unsigned long, unsigned char, that are just meant not to take negative values. So all this thing is doing, all this function is doing is taking all the arguments and just printing them out. Printf is probably the most widely used way of doing output in C. And the way it works is there's a format string, which is the first argument. And the format string, you can write any kind of text in there that you want, but things that begin with % are special. So %C represents a character. That means the first argument should be a character. %D represents an integer. It means the second argument should be an integer. And you can see I'm not violating those rules. LD is a long. LLD is a long. Weirdly, F is both a float and a double. It's just a weird thing from C's past. And then U is an unsigned integer. LU is a long unsigned integer, and LLU is a long unsigned integer. So I'm just printing out the values that I received that were passed to the function. Does that all make sense? Is anyone not following? Is that all right? Yeah, it's going to get more fun, I promise. So you see a simple function call here where I'm passing to character A, -3, 4, 5, 5.6. These are the 2 floating point numbers, and then the unsigned numbers at the end. And all it does is print those out. I'm just whipping through how to do conditionals and loops and so forth. If statements in C look exactly as you see. Boolean expressions in C are actually numeric. So the thing inside parentheses is evaluated, and if it evaluates to 0, it's false. If it evaluates to anything besides 0, it's true. So the A equals 0 will be 0 if A is not 0, and will be 1 if A is equal to 0. So true or false are 0 and 1, but it's really more broad than that. 0 is false, everything else is true. Does that make sense? That's much less stringent than languages like Java, where you have actual Boolean types with true and false, those actual values. But you'll see it's pretty handy, actually, because I can do arithmetic inside of here, for example, and check the result all in one step. So I'm checking to see if A is 0 or if A is 1, and I have an else here. Yes?
Is that the thing for whenever, like, you're returning a function? So, like, whenever a program will say return -1, is that also? Yeah,
so you'll see this pretty soon, but like when you open files, I'll just show you now. There's a program that you have that does file IO. One of the things that it does is open a file using fopen. So what's happening here is I'm calling fopen. The return value is a file handle that controls the file. So that it's checking to see if this whole thing is non-zero, because fopen actually returns 0 if there's a failure to open the file. So you see, I can do the assignment and the check all in one block. So the way this works is FD is assigned the return value from open, and then the whole parentheses are checked to see is it 0 or 1, or is it 0 or anything besides 0. Yeah, we'll come back to that later. I emphasized this in the previous boot camp, but I'm going to emphasize it again. You technically when you do if statements, imagine you have like int n equals 7. I can technically do this. where this assumes I have, well, I can just do a printf here. Right? I can technically do that and leave the braces out. Don't do that. Right? Always put the braces in. So C allows you to have braceless things only when the body is a single statement. But the reason this is a horrible programming practice is that when you decide, oh, well, I want to add some supplemental information, right, and print out some other stuff. See, I'm using Emacs, and Emacs is smart. It sort of won't let me indent that to be inside the if statement. But a stupid editor like Nano or something is gonna let you get away with doing indentation like that. And this is inside the if statement. This is not inside the if statement. That it's just not very much extra work to always put the braces in. And almost every modern C programmer will tell you, like, don't just make life harder for yourself by refusing to type 2 characters. So making things proper blocks inside of braces eliminates the Python madness that the world encounters, where someone is evil and takes your Python program and does this and eliminates all the leading space, and now the semantics of the program are actually broken. If you don't do that in C and you leave it like this, C doesn't care if you do even stuff like this. It's perfectly fine because it's all parsable. Does that make sense? And if you have a proper editor, when you decide that's a bad idea and I want to put it back, if you have a proper editor, it's going to do all the indentation for you. Like, it can be fixed rapidly and there's no semantic change. So no matter what you think about Python's not having braces, you're wrong. It's not okay. These languages in the 1960s were tried out that used white space as a mechanism for deciding where blocks existed and where they didn't, and it was just utterly abandoned until Python came along and decided to dig that grave up and do it all over again. Okay, you can hate me if you want, but it's still wrong. So that's an if statement. Any questions about that? We needed to see common control structures and stuff to know how things are going to go later. While loops are very straightforward. They look like ifs in terms of this condition is still a 0 or anything else situation. 0 is false, right? Which means the loop will stop, and anything else is true, which means the loop will continue. So if A is 0, the loop stops. If A is non-zero, the loop continues. So this is kind of cool because I don't need a Boolean or anything. I can just have the variable A and just evaluate A. And when A becomes 0, the loop stops. So the idea here was that I set A to 5, right? And the loop will decrement A and then print the value of A and decrement A and print the value of A. And when A becomes 0, the loop stops. Okay. There's also a bottom tested version that looks like this. And you may find it easier to follow along on the paper instead of looking at the screen. It's your choice. The bottom tested loop just does the test at the bottom. And it does it while the loop continues while this happens, while this condition is true. The difference is this one will execute 0 or more times. This one always executes 1 or more times because the test is at the bottom. Does that make sense? Any questions about that? Okay.
Could you still do while A for the do while loop?
Mm-hmm.
Okay.
Yeah, I just did this to indicate, just to give a different example. Mm-hmm. Yeah. For loops are very, very common in C, very, very common. You have an initialization that only occurs one time at the very first time you encounter the for. You have a top tested condition here. The loop will only proceed through if this condition is true. And you have a bottom executed statement here that's usually used to increment or decrement loop control variables, but this happens at the bottom. So when the for loop is first encountered, I is set to 0. There's a check to see if I is less than 10. If I is not less than 10, the loop doesn't execute at all. If I is less than 10, you go into the loop, and then at the bottom where you encounter the brace, right? You execute the I++, and then go back to the top and check this again. But this initialization doesn't happen anymore, just one time. Does that make sense? It's kind of as you would expect, I think. For loops exist in most languages. Is that all right? So there are some eccentric behaviors in C. So you've probably seen something like case statements before. They're used to check lists of values to find the one that corresponds. So you see switch A, that means I'm testing based on the value of A, right? And it has to be an integer in C. You can't have strings and stuff in here. Just numeric values. So you have switch A, and the cases are 0, 1, 5, and then default is anything else. Does that make sense? Now here's the thing that you may not be used to. The breaks are required. First of all, you don't see any braces inside of here. So I can have as many statements as I want. I can have as many statements as I want in one of the cases with no braces. They're all inside that individual case statement. If I leave the break out and the value is 0, like the 0 triggers, if the break is missing, you cascade through until you find a break all the way down, ignoring the cases. So it means if the value is 0, I'm going to see in my modified version, A is 0, and I'm going to see A is 1. I'll see both of those messages come out. So the break is what makes it stop. Does that make sense? Now that you may not like that, but the reason that's there, it's very common that you'll have this. You'll have something that looks like this, right? Where you enumerate a bunch of cases that all trigger this message, and then the break makes it stop. Does that make sense? Yeah. If you forget the breaks though, and you don't intend for there to be cascading, you're going to have weird behavior that you don't like very much. Because often these wouldn't be print statements, it'd be some computation, and you'll have complete madness if you forget the breaks. You don't have to put the break in the default, obviously, if it's at the end. But the reason I trained myself after too many years of C programming to always put it there is default is not required to be at the bottom. It can be anywhere. So just always put the break. There's a bunch of things you can do to make your life easier and reduce the number of mistakes you're going to make. So does that make sense? I've been programming in C long enough to have made every single mistake. So I've developed some habits that make that not happen anymore, I hope. All right. Anyone seen the ternary operator before? The question mark operator in C? You've seen it? Raise your hand. Okay, a couple of you. This is a shortcut that you can use sometimes to not have to use a full conditional, an if conditional. So this if A equals 5, then I equals 7, else I equals 9 can be written in C like this. And what happens is you're assigning to I, right? But you're asking a question. Is A equal to 5? That's the double equal sign. That's the question. If the answer is yes, use 7. If the answer is no, use 9. And so I gets to be either 7 or 9, depending on whether A is 5. Does that make sense? It's much shorter to write than a big block of if statements. But arguably, if you use these too much and if you nest them, it can be a little complicated to figure out what's happening. And I've given you an example here. Right, there's a bunch of nested ones. Right, well, this one's not too hard to read, I guess. You can kind of see what's happening here. But I'm actually using the ternary operator to give a value that's going to be used as an argument for printf, right? So not A is true only if A is 0. So the value I'm going to return is 0. The string is 0. The colon is the alternative. Otherwise, if A was 1, the value is 1, 5, either 0 or 5. You see what happens here? Okay. So you can be a C programmer and hate the ternary operator and never use it. I use it a lot because this print statement is much easier to write than having to write a nested if statement to print a different value for each of these things. It's much more straightforward. Any questions about this? all right? Now, something important is that the function that we had here, all of these values are passed by all these arguments are passed by value, which means the function can't change them. The function can print the values or manipulate them locally, but any changes will not be reflected outside the function. So in some of the next examples, we're going to figure out how to deal with that problem. But for now, all you know how to do, at least in terms of this boot camp, is how to pass arguments by value only. Okay. Any questions about this at all? All right, so next up on your list is just a quick diversion and a simple example that uses command line processing. So look at command line.c, which looks like this. It's pretty short. If you're wondering what argc and argv are, these things that you always place inside of the main definition, argc is an integer. It's a count of the number of command line arguments. The minimum number is 1 because the name of the program is always argv of 0, meaning the first element of the array. This is a string, an array of character strings, each of which represents one spaced or tab separated argument. And then I can walk those like this by starting at 0, because you have argv of 0, of 1, of 2, it's an array. Going up to argc, but not including argc, because if there's 6 command line arguments, they're numbered 0 through 5. Arrays are always indexed from 0 in C, and you can't change that. Okay? And then I++, because I'm moving on. And puts is simpler than printf, and then I'm not doing any formatting. I'm just literally printing out a string. So I'm printing out argv of 0, 1, 2, 3, 4, etc. Does that make sense? So this one probably is easier if you just see it work. So I'm going to split the screen in Emacs here and open a terminal inside of Emacs so you can see this run in here, right? So if I run command line by, oops, sorry, I was running this on a different kind of machine. So, oops, don't do that. So if I run this just with seemingly no command line arguments, the command line argument is command line, which is the name of the program that ran. So this is cool because C programs can figure out what their own name is in case they want to know that, right? If I do command line arguments like this, I just see them as 1, 2, 3, 4, right? And if I want them to be grouped in some way and not be considered individual, you have to delimit them with double quotes. There's really nothing more to it than that. Lots of programs you run at the command line in C need lots of command line arguments to do their thing. And so this is used all the time. So just get used to it. Any questions about that? So see, you don't have to leave Emacs, right? You can have a fireplace in here, and there's a local psychiatrist that can do psychoanalysis, and there's a thing that counts down until Cthulhu destroys the earth and we all die. And I mean, all this stuff is built in. So email, web, you can surf the web, do anything you want inside of Emacs. Yes. So yeah. So then there's this horrifying example called lots of init.c. So we'll look at that next. This thing is showing you all kinds of crazy C stuff, hopefully trying to sort of expedite understanding pointers, because it's unlike C++, actually, where if you use the C++ like standard library with vectors and all that stuff, you could basically write C++ without using pointers at all. In C, it's absolutely impossible to avoid pointers. So if you find that, oh my God, I can't live with pointers, you can't do C programming. You have to do something else. Okay? It's absolutely required. So I'm going to try to illustrate some of that now. We'll start just in main here and just ignore the functions that are on top for now. I have an integer and I assigned it 7. I have an integer in B and I assigned it 3. And I have an integer pointer, which means this points to the box that contains the value of B. So B is think of B as a box that can hold an integer variable, and I've placed 3 inside the box. C being an integer pointer, the star C equals address of B means I'm pointing at the box that B is in, not the value of B, but where B lives. Okay. We'll come back to that in a second. Now, look at this. I can do mem copy. This if you're used to programming in Java, this may make you like feel sort of sick, because we're completely bypassing the type system here, right? And saying, look at the memory address where B lives. That's the pointer, that's address of B. And look at the memory address where A lives. That's the box where A lives, right? Memcopy peeking inside the box of A and copying byte by byte each individual byte that makes up the value of A into B. And you know, the size of int is how many bytes are being copied, because they're both integers. So rather than saying B equals A, I can say mem copy address of B, address of A, size of int, and that actually moves the individual bytes one by one and duplicates A into B while leaving A alone. Does that make sense? Now, this is a stupid thing to do, and you would never assign integer variables like this, but I want to point out the mem copy things, the ability to move blocks of memory around and do stuff like this is why you can write things like operating systems and device drivers in C. That's why we're using C in the first place, right? Is this okay? Yeah.
So for the int pointer C, it's pointing at the box that holds B. And what if I were to just write C equals the address of B, like without the pointer? Like what does C being a pointer do?
So C, C's type is an integer pointer. So the star C means it's not an integer, it's a pointer to an integer. Its native type is totally different, meaning it points at something. It is not an integer. And one interesting way of thinking about this is the int star C. If you think of how big that thing is, it's 8 bytes, because on a 64-bit machine like you guys have, it takes 8 bytes to have a pointer that can look anywhere in the address space. The integer is only 4 bytes. So the integer A is this box that has some value inside of it, and we put the value 7 in there. What C is doing as a pointer, if I don't assign C anything, if I just said int star C and it didn't initialize it, it's pointing at some random thing. And that's probably not what you want in general. So you trying to use C directly would probably result in a seg fault, because this is pointing at a random memory address, probably not some memory address that your program owns. But when I initialized C to be the address of B, what happened is C is now pointing at the box. It's not the same as A, which directly represents the value 7, but it's now located. You've essentially located where A lives, and you're pointing C at it. This dereference of C, putting a star in front of C and doing like star C equals 13, peeks inside the box and wipes out the value and changes it to 13. So you want to be cautious and use this when it's appropriate and not when you don't have to use it. This is the only way you can pass arguments by reference in C, as you'll see in a minute. If I want to pass arguments to a function and change them, I have to use this. But using it sort of weirdly, like I'm using in this example, creates aliasing that's not fun to debug if you forget what's going on, because it means by aliasing C to the box where you know A lives. Sorry, it's the box where B lives, right? Same idea, different variable. By aliasing C to the location of B, I can modify B through C without ever touching B. So if I do star C equals 9, B changes. And imagine I change, I did it, I think in here, if later I do like C equals address of A, now if I use star C equals 17, then A changes. You can create all kinds of madness with variables changing without referencing those variables, which is fun as like a magic trick, but it's not fun to debug as a programmer, right? Because we're looking at these examples on one screen, but 50,000 line C program with this going on all over the place, you'll never figure out what the variables are doing anymore, right? Particularly if you didn't write the program. Is this okay? All right, cool. So mem copy makes sense. It's a very, very low level memory copying operation. You can copy literally any memory anywhere you want as long as you own it, and any size that you want. Is this okay? All right. So we're printing out the values of A and B. We'll run the program in a minute. We're changing the value of B here with star C equals 9. So B has just changed to be 9 now, right? And I'm printing it out so you can see that. Now you may not like this at all, but you have to get this under your C brain immediately. All pointers are arrays. So C is, and it's a pointer, but it's also the name of an integer array. And if you're wondering like how many valid elements it has one valid element because I pointed it at a box that contains one integer, and that's all the storage that's allocated. So B is the same as C of 0. The 0 element of the C array is B. Why? Because I pointed C at B, and that's a single element array now that has one index that's valid, which is 0.
So
I know, right?
So before C of 0 at the point where its pointer is C equals 9, C of 0 would be 9. Is that right?
C of 0 would be 9.
Yeah, and then
yeah, that's
when
correct.
you say it's 13, then it's 13.
That's correct. Yeah.
Okay.
It's okay. The reason this works is that let's just take a tiny diversion and look at something else that's a little simpler to understand. If I have some integer array like this, I think it's understandable that that's an integer array with 5 elements in it that index 0, 1, 2, 3, 4. Does that make sense? The name A is a pointer. It's a constant pointer to an array of 5 elements. So I can't change A, but I can certainly point some other integer pointer at it. Now A and B are pointing at the same block of 5 elements. This thing is the same as this thing is the same as this thing. So A of 0, that's the 0th element, but the 0 offset from the pointer A and dereferenced is also A of 0. Let's give it a value to just make it very clear what I'm doing. Imagine I did something like this. This is 17. This is 17. This is 17. Does that make sense? How much do you like this? I don't know. I can't tell. Let's do this. This is 13 now, right? This is 13. This is 13. And as you probably have guessed, Emacs is fighting me for indentation rights now. So all of these are 17. All of these are 13. Now you might wonder, and this is going to have to be figured out thoroughly to make your life in C land good. When I add or subtract things from pointer values, it's not subtracting one byte, it's subtracting one thing, one size thing that it's pointing at. So you get an automatic kind of hidden multiplicative factor there. That means the integer at the one position in the array. It doesn't mean one byte past A. And the reason this works is that the way C works is that the type of this B thing is an integer pointer, right? Type of this A thing is an integer pointer. Integers are 4 bytes. So this is literally incrementing A by 4 bytes to get to the next value. So if you think about how the array is stored, if it's an integer array, right, here are the elements in the array, but there are 4 bytes inside of each of them. So when I say A plus 1, I really do want it to be there, not here. So it means pointer arithmetic is exactly the same as array index.
So the A of 0 would be all the way at the left.
Yeah, A of 0 is the first 4 bytes. A of 1 is the second 4 bytes. Okay. Because those are integers. And B is pointing at the same stuff that A is pointing at, so it means the same thing, right? Does that make sense? Now here's what you're probably not going to like at all. What do you think this is? You promised the compiler that you wanted 5 things, right, that look like this. And each of those was broken, right? Now, you're basically going way out here and touching some memory address. It's just whatever is at the memory address A plus 100 times 4, because the size of an integer is 4. So A plus 400 bytes out, that's the value. You probably don't intend that because you didn't ask for that memory. You don't know what you're touching there. You could be touching some other variable that's declared. So I'll tell you that if, in C, the way these are laid out on the stack as they're, as the storage is being allocated, things that are higher up here are at higher memory addresses. So I could have, for example, a float that's up here like E, and by walking off the end of the A array, I can actually trash the value of E. You don't get any compile error if you do this, because C has no array bounds checking at all. And negative indices are perfectly okay. So that just references memory off the back side of the array, which you almost certainly don't own, but it's totally legal to do that. Because all that happens is pointer arithmetic. What does that mean? It means A plus negative 100 times 4. That's so negative 400. A plus, A minus 400 is the memory address that's going to be used to find the integer. So you can look anywhere you want, and it's completely seatbeltless. All you're going to get if you make a mistake and don't really get if you didn't really intend to do that, and in a valid way, you get a seg fault, and that's all. Make sense? So everyone's just going to grab their pizza and run away and quit, right? No. Once you see why it's useful in many cases, it won't be as scary, I think. It'll be fun. All right, so does that make sense? Pointer arithmetic and arrays are the same.
Is there ever a point to go past the array?
Yeah, to do exploitation.
Oh, okay.
You definitely don't generally want. It's not legal. The C standard says no. It actually says the behavior is undefined. So you definitely don't want to do that. It's done in exploitation a lot to make software misbehave, like nation state warfare and stuff. But in general, you want to keep your array bounds inside the array. And you might wonder, like, why isn't there array bounds checking? It's because C is designed to be a systems language for writing operating systems and other fast things. And if you want array bounds checking, you have it in Java, right? The reason Java is slow is that Java, every single array reference in Java is checking to see if the array bounds are in bounds. And this is over and over and over. Other alternatives, don't make any mistakes when you do programming. Then you don't need to do that and things can go fast. But that you are trading off arrogance for safety, right? Does that make sense? So you can either have something that's totally safe and slow, or you can have something that's totally unsafe and very, very fast.
Line 46.
Yes.
When you get C pointed to the A's address, is that still point to B?
No, you've changed
It just
point.
connects.
Yeah, C can only point at one thing. You just move the pointer around. Yeah, and again, please don't model good programming off this particular example, but the reason we're doing this example is that you need to quickly come up to speed on pointers and arrays are the same, right? Because otherwise the other examples are really not going to make a lot of sense. And that's why we can spend as much time here as you like. Here's something else that you could do here that would be really difficult to do in Java. Imagine I just want to see the individual bytes that make up the memory that's holding the value of A. I can do that by using I want to use an unsigned char star. That's an unsigned character pointer. Why? Because an unsigned char is a 1-byte value. And I'm basically going to walk through the individual bytes that make up A and print them out. And this weird thing I'm doing in printf here that you probably haven't seen before, %02x, means I want to print the single byte as a pair of hexadecimal digits prefixed with 0. Sorry, prefixed with 0. So if the value is like in hex 1, I'll see 0, 1. Is that okay? What does unsigned mean? It means cannot contain a negative value. So a regular char is -128 to 127, and an unsigned char is 0 to 255. So here's a loaded question. Why do I use an unsigned char star here? I'm using this peak thing, right? Peak is an unsigned char star. But I'm looking at the bytes of an integer. Why can't I use an integer pointer there? Specifically, what'll happen? Oops, sorry, that's really bad behavior. What'll happen here with the peak of I if peak is not a character pointer, but is instead like an integer or something else? What do you think peak of I, peak of 0, peak of 1, peak of 2, peak of 3 would actually look at? So it's a 4-byte integer, and I'm interested in looking at the individual bytes. So I want to look at the 0 byte, the first byte, 0, 1, 2, 3. Those are the bytes, right? What would I get if I didn't use a character pointer here, and I just use an integer pointer? Or peak. Peak is like unsigned. Unsigned int or just int star peak.
You like get too much data at once. You get like the size of an int, so you get 4 bytes.
Yeah. Yeah. Peak of 0 would be the first 4 bytes. Peak of 1 is the next 4 bytes. Peak of 3 is the next 4 bytes. I would walk off the end of the integer. Is it clear why? So I told you anytime you do pointer arithmetic, which is the same as array indexing, that's what we were just looking at, you'd walk off the end. So let's draw a picture. So the value of, okay, here's A, right? It's a 4-byte integer. So it has some value. The value is 13, for example. It actually looks like this, and we'll see why in a minute, because of weird storage on Intel boxes like we all have here. But anyway, that's an A. This is A, right? And we've pointed peak at this thing. Since peak is an unsigned char star, it's an unsigned char star, which is a character pointer. The size of a character is 1, so the increment is 1. So when I look at peak of 0, I'm looking at that character, that single byte. And when I look at peak of 1, I'm looking at that one. And peak of 2 looks at that one. Now, this thing is an integer pointer. Peak of 0 would look here. Peak of 1 would look there. Peak of 2 would look there. And peak of 3 would look there. Because it increments by 4 every time. That's why it has to be an unsigned char. Because you may wonder, like, why on earth an unsigned char? Really, it's because it's helpful to think of unsigned char as a byte, a byte type. It means one single byte. That's really what I want, because I'm looking at individual bytes. It's just I don't have a byte. I only have unsigned char. So use that. Right.
No, I specifically unsigned as well.
Because we're trying to print hex digits out, or hex values between 0, 0, and FF. And we just don't want signed stuff to mess that up. And we're going to run this in a minute. You'll see exactly what's happening. But is this okay? Okay. And then here's something a little bit easier. I told you that unsigned char are char. It's just a small integer. So if you want to know what characters, if you're not using it as a tiny integer to do arithmetic, and you're actually interested in the characters that it represents, you have to go look at an ASCII chart. So if you look at an ASCII table, they're all over the internet. You can print one out, fold it, and put it in your back pocket and memorize it. These are the values. They start at 0. The ones down here are non-printable. And they're mostly old arcane things that work with like weird terminals that don't exist anymore, like bells and stuff like that. But A's and B's and all the lowercase characters and everything are in this table. So the number that you see here, this is the decimal number, and the number you see here is the hex value. But I can just use those numbers directly. So when I put char, that prints out one character. When I put char 97, right? Or I put char an A in single quotes, that's exactly the same thing, because lowercase a is 97 on that chart. So that makes sense. Now, you don't really, in general, want to say put char 97 if you know that it's an A. But there are going to be some nice applications of this, because if I want to put char A in lowercase, right, I could just subtract off the uppercase value and add the lowercase value like this. And I get A, assuming A is between A and Z, I get a lowercase version of the character that's in A now. If A is like a B, right? By subtracting off if A is an uppercase B, by subtracting off big A, I get 1. And when I add that to a small a, I get small b. I mean, a small b. Yeah. So it may seem crazy at first, but it's actually really cool and lets you do things like that don't require like if statements or switches or something like that. C is supposed to be very efficient. You have something in mind that you're trying to implement. It's not going to give you a bunch of help in terms of providing like vectors and hash tables and B trees and stuff. You might have to write that stuff yourself, but what you're visualizing you want to do, you can simply do without the compiler telling you can't do it. If I decide I want to change the 7th byte in a floating point number to be some other number, just to see what happens to the floating point numbers, it sort of blows up and becomes something else, it's totally possible to do that. You just point a character pointer at the floating point number and change like C of 7, and whammo, the 7th byte changes. 8th byte, 0 through 7. Yeah. Okay. Any questions about this? Still okay or not okay? I don't know. Is it?
My head's starting to hurt, but
It's supposed to hurt a little bit. Right? wait till later and see how much it hurts. There's pizza too. We can also have these. Take a small break. All right. So this is really okay. You're really okay with the pointer and arithmetic, the pointer and array equivalence. Okay, I'm not going to beat it to death if you understand. Look at these two functions now, because we need to figure out how to pass by reference so we can change values. That's in a function. That's really important. You have just look, which has an int a. I'm going to pass the argument into just look by value. So if I change a inside, I see a local change of a. I don't see any. There's no influence on the argument that was passed in. Do you believe that? So specifically, go down and look. I'm going to do this. So you can see both at the same time. Here's that function. Oh, sorry, not quite. Here's that function. Over here, I'm calling just look with a, right? This value is not going to be changed by calling just look, no matter what I do to the argument a inside of here. And as you know, there's no correspondence here. This could be like z, right? It's just an argument. So it may be better even if the example looked like that, right? So changing z here has no impact at all on the argument that I passed in here. Yeah.
Oh, whenever you call z equals 17, what is actually set equal to 17? Like a register or
a local variable called z,
okay,
which is this argument.
So it creates a new variable whenever it.
I mean, the arguments are variables. The only question is do they have any connectivity back to the other side? So the only connectivity here is that whatever value I pass in to just look is dumped into this z, and then I can see it, I can change it, I can do whatever I want, but there's not going to be any change in the argument that was passed in on the other side. Does that make sense? So that's just like passing by value. You see that in all kinds of languages. Change is different because you don't see an int here, you see an int pointer. So I'm actually passing in the address of b to this int pointer. Now, if I say star b, that's this thing, star b equals 37, I actually see the change over here. Because what I passed in is something that's pointing at the box where this b lives. And again, I think it's going to be better. You guys probably understand scope and stuff, but if we just want to make this a little easier to not get lost in. That differentiates the b. One's a b, one's not. I'm passing in the address of b, which means y, this integer pointer y, is pointing at the box where b lives. So when I dereference y and change it, I'm changing b. This is the only way that you can change values in functions in C. So there's only two parameter passing modes. You pass by value and you don't see changes on the outside, or you pass by reference and I see changes on the outside, or pass by address rather.
So can you give me an example of the value being changed? I don't quite understand the difference still.
So in this case, you have a separate box called z, and all the function call does is dump the value of a inside the z box. Now I can change z, I can do whatever I want, but I have a local z here. Int z is a local variable. I can change it, I can look at it, I can do whatever I want, but there's no reflection outside this function. So the scope of z is just entirely inside this program. Now here, the scope of y is inside of here too, but the value that got dumped into y is the place where b lives. So now when I change y, if I just said y equals 37, there's no change to b. But if I dereference y like this, then I do change b.
Oh, so in the first example, a isn't getting changed. And
no, not at all.
And so it's just going to.
Yeah, first example, I have a is a box and z is a box. And whatever was in here, like 17 or something, gets copied in there, and then whatever, right?
Yeah.
In the second case, I have a B out here, which has some value. And the thing I've dumped in the box over here, right, is a pointer that's pointing at B's box. It's address of B. That's what's in here. So if I dereference, I actually change the value of B.
So
That's
now
the star Y thing, yeah.
yeah, so A isn't being changed, but B is.
That's correct.
Okay.
Yeah. So it may help to just run this guy and you can see some things happen. Now you have to kind of, sorry, that messed up everything. Let's do that again. Go back over here and you can just kind of follow and see what's happened here. So, here, these addresses, I'm just trying to show you like where all these things live, like A, B, stuff like that. So you see the address of A is this horrible thing. That's just the memory address where A lives. B lives at this memory address. I assigned C to be the box where B lives. So I would expect that what C's value, notice I didn't dereference C or anything here. That's just naked C. C is the same as B because, right? I printed address of B and that's what I assigned to C. So those are the same. And then you see me doing the mem copy thing, right? And I've ended up with A and B the same. That's this thing. Then I've done these dereferencings and so forth. And then more importantly, maybe the function calls. Like I passed the value of A, I changed Z, it had no impact on A. That's expected. I changed Y, I dereferenced Y and changed, and that actually was reflected back into B, which is really important. And if this helps, you can sort of see those function calls here, like here. There they are, right? And then here at the top, this is the change thing that's being called, and this is the change thing that's being called like here. Okay. That's all right.
Makes more sense now, thank you.
That's the hope. Do you guys need a slice of pizza to like reinvigorate yourself? Just sitting there. You could take like 5 minutes, you go gulp down a pizza and come back.
Do you guys?
Does anyone want a slice of pizza? Anyone votes that we're stopping for pizza? No one wants pizza. You'd rather have C?
I want pizza at some point, just.
Can we have pizza in like 45 minutes?
Yes. Okay.
My mom.
Wow, you guys are they have some energy. That's awesome. Yeah, great. So that's lots of it. Here's string stuff. So look, just go forward, find strings.c. That's this one. This is not all the C functions by C string functions by any means, but these are the ones that are defined in string.h, which I told you you almost always are going to include that. Here's the depressing news, and the only thing I absolutely hate about C, there's not too many things. The list is basically one thing. C doesn't have a native string type. So you can't have strings where I say like A equals B, strings A and B, where I say A equals B, and I can't say things like A equals B plus C to concatenate the strings together. When you do that in Java and Python and Go and everything, I feel kind of sick inside that you can't do this in C because it's really annoying actually. But it was decided, in 1970 essentially that they just implemented strings as character arrays, and so they're not a first class type. they're just blobs of memory with characters in them, and a null character that's a binary 0 that's terminating the end of the string. It's a very simplistic situation. That kind of sucks a little bit, but it is what it is. So here, the way to initialize a string to nothing, this is a string. A string is a character array. That's all it is. The way to initialize a string to nothing is to drop the binary 0 character in the very first position. That means the string has nothing in it. So all the string is in this case is 512 characters max, and one of those has to be a null terminator, or else the string functions will misbehave and your program will crash. You're required to null terminate things. Now the C functions that do strings do null termination, but the things you're passing into them better also be null terminated. So string cat takes the string buff and adds to the end of it high. So it has, here it's nothing, here it's high, and now I've appended on the end of there. So there's a space here, right? So it's high there. Okay. String len indicates the length of the string, not including the null terminator. So the string is literally, the length is literally however many characters hi space THERE is. Period. THER period. Okay. Here's a function that locates the first occurrence of the single character that's specified. So this gives you this is a character pointer, right? So this is another string actually. It gives you another string, but it's sharing the same memory. The first occurrence of T, and if location is null, it means strchr didn't find a T. Does that make sense? Now imagine it did find a T. Where do you think that? How would I search for the next T? So just assume for the moment that I did find that location is not null. I did find a T. How do I find the next one? Imagine it's in location 2 for the second T. How would I find it? Something. What would this something be? Start searching right after the last place you found a T for the next T. Now it's really important that what you end up with is not a bunch of strings here. There's one string buff, right? That's the guy that's got all the storage. If there's a T here, right, location is pointing there. And if there's another T out there, the second location is pointing there. But the cool thing is, since the null terminator is here, if I use location 2 as a string, it's basically this string. And if I use this as a string, it's this string. And if I use buff as the string, it's this string. So that's the cool thing about pointers. I can put them all over inside of a string and have a whole bunch of different sort of substrings all indexed permanently, right? It's okay. Surely you like that part.
So now if you wanted to just print there instead of hi there, you could.
Mm-hmm. Yeah, if you wanted to print there, you could literally just print buff plus 0, 1, 2, 3. Buff plus 3 is there. Yeah.
You would dereference location with the ampersand, and then that would print.
That would be the character that's at that location.
How would you get it? You would have to cast it to a.
If I wanted to see the T that I just found here, I could look at this. Sorry. If it's not null, right? If I did this. Oops, sorry. If I did this, the output here is T.
How could I get the output to be there?
Huh? Oh, sorry. Yeah, going back up here, if I actually wanted there, I would just do this. This is buff plus 0, buff plus 1, buff plus 2, buff plus 3. So buff plus 3 is there, and it's null terminated because that's at the end. So the bad news is there's no C string type. The good news is that C strings are just blobs of memory that I can do all kinds of pointer crap with and do fun stuff. So you don't really miss A equals B plus C if you just get used to using the string functions. And there's a bunch of tokenization functions and all kinds of other stuff that's actually really cool. So I'm going to just fix this so I don't blow up this boot camp next time. So look down here. This is a less ugly way of finding there. str finds this, it's a substring search instead of a character search. So strchr looks for one character, str looks for a string. So now location is pointing at the there, and so if I print locate, if I printed location, I would just see there. And this is wrong. It should be fixed in the future. Sorry about that. And yeah, here's a comparison function. These are really, really important. Comparison functions in general in C for sorting and all kinds of stuff, which you'll see in a little while, operate under this, all under this uniform principle. I pass two things into a comparison function, and the return value is negative if the first thing is smaller, 0 if they're equal, and positive if the first thing is bigger. You should think of them as being kind of subtracted in a way, right? There's strings you're not subtracting, but you know what I mean. If the first string is lexicographically smaller, I get a negative return value. If they're the same string, I get a 0. So what people will often do, you know, you see like the CMP is here, right? They'll do if not CMP to indicate that the strings are the same. Looked at a different way, a C programmer, if you were just interested in knowing, is the buff equal to exactly high there, I wouldn't write all this. I'd just do this. Why? Because string CMP is going to return a negative, it's going to return a 0 value if they're equal, which will make that Boolean condition true in C. Not 0 is 1, so that means the strings are equal. So you may kind of feel like, well, it should be if string compare means they're equal, but that's not really, that wouldn't really work, because you want equality, and you also want less than and greater than. So this does really make sense. Just don't forget the not. It's okay. So that anyone that's an experienced C programmer would write that. You wouldn't make a separate integer variable and all that stuff. You just check it that way. Here's tokenization, which is pretty cool. So I set to free and string to be both equal to the return value of string dupe. So what string dupe does is takes milk, bread, cheese, and coffee and makes a copy of it and returns a pointer to the copy. Okay. Then tokenization is really simple. There's a thing called string set. That means strings separate. And I want the token to be, this can be an arbitrary list of delimiters, but I just made it a comma. So I'm just busting apart the string delimited by commas. And I can call this thing repeatedly. It'll return null when it doesn't find anything else that's delimited by a comma. But each return value that's not null will be a pointer into the string that is the location of the next token. And if you look at the man page for string dupe, you're actually required to call free on the thing that it returned, because it returned a memory, a blob of memory that was a copy of a string. There's no garbage collection in C. You have to give memory back when it's appropriate. And this is one of those times that you have to do it. If you forget, nothing's going to crash. But in a long running program that constantly just dumps memory like that and doesn't return it, you'll run out of RAM and die, and the program will die. Okay. For simple like one-off programs like this, it wouldn't matter, but in a production thing, it really wouldn't matter. In a spacecraft, it would really matter. Spacecraft runs out of memory and the control system dies and it crashes. So, and the control system won't be written in Java. So when you run this, you'll see the tokenization happen: milk, bread, cheese, coffee. So you didn't have to do any fancy loops or anything. You just rely on the C standard functions. And there's gobs and gobs and gobs of them. There's all kinds of string functions. You have to really look at the man page. So, questions about this?
Yeah. When you have buff and the index is 0, the beginning, that represents, does that also represent the whole string? Right?
Yeah, you're tossing around buff as the string, and by writing a 0 here, you all the string functions terminate, they stop processing and they see a null. So that means that the string is empty.
So let's say you want to change the character H, capital H, to a different character. How would you go about that?
Yeah, sure. Yeah, so if you did this assignment, right, then you can literally just say buff of 0 equals like lowercase h.
And that wouldn't work for that, wouldn't it?
No, because it's literally just a blob of characters that is an array numbered, they're indexed 0 through 511.
Okay.
So there's no ways of doing like easy insertion or anything. If you want to like move some of the string around, you have to write loops to do that. It's just a block of memory that you can put characters in. And all these string functions are just fancy manipulation functions that are always relying on there being a null terminator, a null character to indicate the end of the string. Yeah, does that make sense? Any other questions about string stuff? Is this okay? Fine. Okay. Here, the next thing in your pile, probably, I think it's mostly in order, is structs. And this shows you how to do what are essentially, they look basically like objects, although C is not object oriented, so don't really call them objects. They're just boxes that contain, they're complex types that contain multiple fields. So a person in this case, you see type def struct person. This is a type that's a box that has an integer, a 15 byte, 15 character string, and another integer inside the box. And so I can reference these individual fields inside the box when I create a person. I can declare something of type person and then basically reference age, name, and dead. Right. Is that okay? So, and there's some other struct types here too. We'll just look down here and see what they look like. This is kind of cool. Global variables in C are always initialized to 0, whether you initialize them or not. So that means if a global variable, that's something not inside of any function. If I said something like int z here and didn't initialize it, globals are automatically initialized to 0. That's not true of variables that are inside functions. You may not like that, but that's just the rule in C, and it's in the C standard. So anything that's global is automatically 0. Anything that's in a function is going to be some random value unless you initialize it, okay? But the reason this is kind of cool is here's a global person that I've declared. It's literally called global person, right? And I'm initializing with this initializer list. And in this case, I put a dot in front of the name field. So I'm gonna let you see what a person looks like. Sorry, this is bad. Let me just move the person closer to where it should be. Now the person is down here. Okay, so I have a type called person, and I've declared something called global person of type person. C is case sensitive. There's no rule about making types uppercase and stuff, but most people try to indicate that things are types by uppercasing them and using lowercase for variable names. Okay. So I have a person here, and this global person, and I said dot name equals Cecil. Okay, that initializes this. The age and dead automatically get initialized to 0. So the age is 0 and the dead is 0. You're not going to see any real applications of this tonight, but if you go read operating system source code, it's very, very common that these big complex structures are initialized like this to rely on the fact that it get all this initialization for free to 0, because there's lots of fields that should start at 0, and I don't want to write like a dot blah equals 0, blah, 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 and, you know, hundreds of initializations when I can just whammo initialize the fields I care about and all the rest are 0. Is this okay? Okay. So what I'm doing here is printing out the things that are associated with that global person, and the way you look inside of a struct type and get at the individual fields is using these dots, right? So dot age, dot name, dot dead. Okay. So there's other structure things in here, but I want to look, this is important. Pointers are going to have to be in here somewhere, right? You knew that would happen. Let's look at this favorite thing. See the S favorite that's here, and there's a color inside, and there's a number inside, right? So let's do this maybe. I have a pointer. I have an S favorite, and I have a pointer to an S favorite. S is just an S favorite, and S1 is a pointer to an S favorite. So to initialize S, I could just say S dot number equals 3, right? And I can say string copy S dot color to be purple, and I can print those things out. Okay. Does that make sense? But look at the initialization of S1. S1 is a pointer to an S favorite, right? Meaning it's not pointing at anything. And all you've seen so far is me point pointers at other variables and like steal their storage. But what if I don't want to do that? I just want to start with a pointer and give it some storage so I can put something in the box. So I give it its own box. malloc does that. So malloc is memory allocator, memory allocate. And I'm memory allocating size of an S favorite. That means now the S1 pointer is pointing at a box that can contain an S favorite. So I could do this, which is kind of annoying, right? I could do sorry. Yeah, I could do like, have this kind of cumbersome notation that looks like that. But this arrow notation gives me the ability to kind of skip that. The arrow says peek inside the box and do dereferencing at the same time. This is the same as this, but the S1, yeah.
What is S1 dot number? Like without anything around it, what is that?
It's one of these guys.
And it's a pointer to that?
So S1 is a pointer to an S favorite.
And then if you put the dot number on it. What is that?
It looks inside and looks at the number.
Okay.
So sorry, it looks like this. Having pizza withdrawal or something. It looks like this. That's the way to get to number. Why? Because you have to dereference S1. That gives you a favorite. Then I can not number it.
Mhm.
But this is really cumbersome notation. And so the preferred notation is this. So C gives you this shorthand, the arrow, which says look inside the box and do the dereferencing for me. So you can either dereference dot number, or you can just say S1 arrow number. And the arrow thing is what everyone will use because it's much less tedious to use. Does that make sense? Is it okay? Not okay is okay. Yeah.
Is there a notation with the arrow pointing the other way?
No. It's okay. So I'm just cleaning this up again so I don't wreck my examples. Yeah. So if you didn't do this malloc, S1's just pointing at a random memory location that you're going to say, treat that as a box containing an S favorite, and you're almost certainly going to get a segmentation fault because you don't own the memory that S1 is pointing at. Yep, go ahead.
So why didn't you have to do this S1 pointer thing for the earlier ones, like the F dot number, F dot E dot number?
You mean like
or
this, for example, here, this one?
Yeah, something
Yeah,
like
the
that.
reason is that this S is not a pointer, it's an S favorite. It's it literally defines a box that's an S favorite. This wants to point to an S favorite, but you have to point it at something that's an S favorite. You could point it at an existing one, but that stuff that I've been doing with aliasing is not really that common. It's much more appropriate to be able to just make pointers and dynamically allocate memory to them. And one reason you'll want to be able to do this is that if I have an S pointer like this and I don't allocate just the space for one S favorite, but allocate, say, 7 times the size of S favorite, now I have a dynamically allocated array of 7 S favorites. I'm not sure that made sense. Go and look at this malloc again. We were here. No, we were here. I told you pointers and arrays are the same. I just made an array of size 1 that's pointing at an S favorite. So there's a box with an S favorite in it, and S1 is pointing at it. It's very easy to extend this to be an array of 9 S favorites by just multiplying the size of one S favorite by 9. Now S1 is pointing at a big blob of memory, and S favorite of 0 is the first one, S favorite of 1 is the next one, S favorite. It really is, C's conceptual model really is simple. You just have to kind of get your brain around the pointer stuff, and you'll see that it's not complicated. It's actually pretty primitive. And once you see that pointers and arrays are the same, pointers and arrays become much, much simpler, I think, to understand.
So with the other S favorite where it's just an S, that one is like fixed. It can only be.
Yeah, and in fact, the cool thing is that yeah, things like S, for example, here, you can't change where it lives. S is stapled to a box that holds an S favorite, and S is just the name of the thing in the box. You can take the address of S to get like where the box is, but you can't change S to point to something else. It's literally like a tattoo on the box that says S. That's where S lives, right? Does that make sense?
What's the size of that favorite exactly? Yeah, is it based off of?
Yeah, it's based on all the things inside. But the tricky thing here, the reason I use size of it, I didn't just add together like 15 plus 4, right? Is that the compiler, for optimization reasons, to make code run faster, may insert some spacing between these fields. So you cannot predict how big an S favorite is without using size of. That makes sense? This is like a computer engineering issue now, but like modern processors can run faster if data are aligned on certain boundaries, like 16-byte boundaries and 8-byte boundaries and stuff. The compiler is doing some tricky stuff to make your program run as fast as possible, but this means you can't really reliably know how big this thing is because it may be spacing these things like an accordion. It's kind of spacing them out, wasting space between to make things run faster. Almost every time you get more speed, you've traded off something like space. Well, you've traded off stupid or space. One of those two things, usually, right? Yeah, bad design or space. I'm not sure that's an all-inclusive list. I just made that up, but I think it's probably mostly true. Any questions about structures? I don't want to beat the structure thing to death, but you're going to write something in a moment using structures. So you're going to have to learn some of this stuff. This is going to be the first time where I get to shut up and not exhaust the voice, and you'll get to write some code of your own based on something I'm giving you, which will make it a little bit easier. But we need to look at one more example before we can do that. Is that all right?
You get to have pizza.
I was gonna say, do we want to take a break here?
I'm gonna let you get a pizza and when you're working on your own thing. I mean, does that make some sense? Like, because that makes it just easier for me to handle. All right, so I'm gonna just fix my example again. So I try not to wreck the boot camp. Yeah, so I'm not gonna go through this one. I'm just gonna point out that because I think I'd rather look at some other stuff, but I've given you bits.c. This is cool in that it shows you how to manipulate individual bits and convert things to binary and blah, blah, blah. So I'll just show you the main only. I'm taking a value of n equals 1, converting it to binary, printing it as binary. So you see the individual bits that make up that thing, right? Changing one bit, changing a single bit, which is bit number 2 in that number, and then showing you what happens, changing bit 12, showing you what happens, changing bit 31, showing you what happens. So in your own time, go and read how all this stuff works. It's complicated because you're doing bit manipulation stuff, and so it's ugly to explain when your brain is already getting tired. But I'll just run it for you. You can just see it, how it works. You see a 1, and this is the representation, and I set bit 2, which is this bit, and I see this representation, and I set bit 12, which is this bit, and I see this representation, and it's dumping hex underneath, right? And I set bit 31, which is this, and that results in a huge number, and this is the representation in both binary and hex. Now, the reason you're seeing the bits in this direction, like this, is that this machine and all these Windows boxes and the new Apple Silicon, all of them use little endian format for integral types, meaning bits are stored backwards from human. You're used to seeing the least significant bit on the right-hand side. It's actually in memory stored on the left-hand side. And there's some architecture, again, computer engineering reasons for this. It's not to irritate you as a programmer. It's because the computer can be made to run faster using this representation. It's okay. Fine. Yeah. So I'm gonna show you one thing here that's hopefully not too mind-boggling, and then I'm gonna display an exercise for you to work on. And you can eat pizza at the same time. So this is a program that reads a one-dimensional array of integers and uses the built-in qsort function to sort them and then output them. Okay? And I don't know why, but I put these variables in there, the A thing, they don't belong, and I forgot to take them out. Okay, so this asks the user for a number of integers that they would like to enter, uses fgets, which is a function for reading one entire line of input from the keyboard, and it's being read into buff here. It's a string, okay? ATOI is ASCII to integer that parses the string and returns the first integer that it sees there. So if the string you typed is like 13 A, B, C, D, E, it's 13. And if you typed A, B, C, D, E, it's 0 because it didn't see any integer, right? So whatever leading digits there are, they're unbroken by non-digit things. It parses that and returns it as an integer. So what I did is into n, which is the number of integers, I got how many integers are going to be entered, right? Now I need some space for the integers because I'm doing this dynamically. So I have a pointer ints, an int pointer ints, and it's set to null. It's not, it's pointing at 0. That's just a safety measure. I'm doing ints equals malloc, n times size of an integer. That gives me an n element integer array. Okay. Then I'm going from 0 to n-1, asking the user to enter an integer, reading it, and then using ATOI to dump it in the array. Then I'm doing something that's going to hurt a little bit. We're going to look at this in detail. Qsort, it's a built-in quick sort that runs really, really fast, right? And it can sort any type, an array with any type of elements. We're sorting ints, there are n of them. You have to give it the size, and you have to write a comparison function because Qsort doesn't understand the type of the thing that's in the array. What it's going to do instead is take elements and hand them to you, and you have to say, are they less than or each other, less than or equal or not or greater, so that it can figure out how to put things in order. So it does all this without actually understanding their integers because your comparison function knows their integers. You'll see what that means in a minute. Then it just prints them out and that's all, you're done. Does that make sense? Okay, so I think that probably the only mysterious thing about Qsort is this, am I right? Like how the comparison function works. Because it's the base of the array that you're sorting, the number of elements and the size of one thing that's inside. Okay. Now here's the trick. Qsort sends to your comparison function the address of two things that are in the array, not the things that are in the array. So if you have an array of integers 17, 15, 2, 1 that's trying to be sorted, it doesn't pass 17 and 15. It passes the address of the box holding 17 and the address of the box holding 15. You're going to see that right here. So here's the comparison function. There are void pointers here. That means the type is unknown, right? The data type is unknown. So this is always what the comparison function for Qsort looks like. You have to do typecasting and say the P1 is actually an integer pointer because I know there are integers in the array. And then I dereference that to see what's actually in the box, what integer is in the box. The dereferencing is done here. That gives me two integers, S1 and S2, and all I have to do is subtract them because I want to return negative if the first one is smaller, 0 if they're the same, and 1 if they're bigger. Negative, 0, and positive. So all I have to do is subtraction, which is pretty awesome. So the tricky thing that gets people stuck is the fact that it passes not the things to compare, it passes the address of the box holding the things to compare as void pointers like this. So first step is get the right kind of pointer. I can't dereference void pointers. Why? Because the size is unknown. The type it's just a generic placeholder for some kind of type. And then the dereferencing gives me the actual integers, and then I can subtract them. And not to confuse you, but just to point out that an experienced C programmer is going to write something like this that's commented out. They're not going to break all this down into steps because I can do type conversion and dereferencing and subtraction all in a one-liner. Right? Figure that out on your own later. But like someone that's experienced, and you will be too, is just going to rip out that line. You're not going to break all this down into 4 variables. You don't need any variables, right? You can just do it in a one-liner. Okay. Is this fine? Why do you look distressed all of a sudden? What part hurts?
It's just a lot. It's a lot.
Okay, but is there any aspect of this that's not clear?
Like conceptually, it makes sense. It's just
That's the answer I want to hear.
I mean,
Okay, so what you guys are going to do is use your printout, type in sortints.c, right? You have to type it to learn the syntax. So you're going to type it. You don't have to type the comments. That'll save time. Like, don't type this version. Don't type any of the comments. Just type the code, make sure it works, and I can see it work, right? And then this is your assignment. I'm giving you a structure type that looks like a car now. I want you to read the value. I want you to read, not this exercise, just this top one. I want you to read in car types, meaning I have to specify year, price, and make and model, color. I have to type all this at the keyboard, right? Sort them by year and then price and output them. Step 1 is go get some pizza. Step 2 is type in sortints.c and make sure it sorts correctly. And then stop sorting integers. Well, you're still sorting integers, really, right? But the structure is along for the ride. And when you're stuck on the comparison function, which may happen or may not, I'll just give you the comparison function, and then you can make the rest of it work. Okay. So rest the brain and have a slice of pizza, and then come back. I'm gonna watch and see if you're sneaking out. So.
All right, someone pizza with pizza and Tommy with pizza.
Is he melting the brain?
I got nervous when I seen my professor walk in.
Oh.
So I think I might be a little wrong with that.
No, you have it right now.
Your intro CS class. Yeah, okay, yeah, I think last year it was nice, it's fun. I like the young ones, they're a lot friendlier.
Oh, yeah, absolutely. Um. oh. It's calm, it's not too bad. It's not too bad.
So, yeah, I mean, the start ones are pretty friendly. The math though is the hard part. It did.
First part, beta happens too.
Focus on math.
Oh, no, I
Second
just
part is hard for the computers.
sometime.
Nice.
My mom
That's all right.
got to do that, so. The
Which
type
math
deck,
are you
so
Popular.
that's one of the things I really confused on. What exactly is the type def doing?
Oh, it's just creating a new
I
type
think.
Okay,
it's all
no
hard.
type of,
car, which is a box that has those fields inside.
so like, same thing as like classes with
Yeah, exactly.
Java.
Yeah,
Okay.
it is.
It's not too bad. I think a lot of rain.
Which one, not for CS?
No.
Yeah.
There is, no, there's so many people that needed the first one, we just made a bunch of first ones. Is it working yet?
Oh, is that working?
Yeah.
Did I get it working? I'm very close.
All right.
Yeah.
Good.
Wise. You didn't let me finish. I'm very close to getting started.
Okay, that's good. Yeah, if you guys get stuck and need some hint, I'll just show you the solution on the pieces of the solution on the slide.
So you open up a terminal. Terminal is like it's like an application like any other. It's like when they got Internet Explorer. It's and so in the box. So this is like a computer that is like thinks it's a real computer, but it's just inside of your machine. So click into it, and then activities. That's what they call their things, and then that's the terminal. Okay. So you can type in commands there, and a very helpful command for you is called VI or vim, which is a like text editor. Actually, for you, probably want to type in nano, which is a name of another text editor, and then you enter. So that will like execute command, and the effect of that command is that now you have a text terminal pulled up where you can type this.
Okay. And I'm just gonna type in this one.
Yeah, and eventually you'll do Control O, and then it'll be like, hey, what file do you want to write to? And then you'll write like stack or whatever it's called, sort.c, sorts.c, and then that's how you like input it, and then he can type out and file it.
Okay.
Yeah, that's another thing. Okay.
Excuse me. Can you help me with that?
Can I?
Can you help me with that?
Of course.
Wrap my head around those are-
Okay, that's fine. Nano is a good start. Other editors are a little bit complicated. So. Yeah, so you just want to start at the very top, leave anything that starts with double slashes out. That's just a comment, and just type it in.
Are you serious?
Yeah, you just type here.
Oh my god. I was looking for what is it?
There's no menu or anything here. This like it's not an ID, it's just editor. So it's just you and the keyboard. And all the commands are at the bottom if you want to use them, but you're mostly just going to be, you have to type that thing. So that like this the optic arrow means C, like holding the control hitting C goes to location and so forth. But you mainly just type it. Yeah, just type away.
What is the ATOI doing in the program again?
ATOI is ASCII to integer. So it takes a string and gives you an integer back. So it just parses the string to find the integer.
Okay.
Yeah, so it lets you type in integers at the keyboard, basically.
Okay.
Yeah.
Is it qualified, something? Yeah, of course.
Is there any specific order you want to year and the price decreasing or increasing?
What's that?
Specific order of the year and
Yeah, sort by year first, and if the year is the same.
you want the decreasing or from the
Yeah.
2021
Oldest year first,
oldest year first.
smallest price first.
Okay. Fail, fail, fail. Fail, fail, fail.
Anyone need a hint? You need a hint?
Maybe.
What kind of hint? Comparison function
Um,
or something else?
honestly, I think I just need to work on it a bit more. I don't
That's fine.
just,
Okay. Don't look up then. Anyone want a hint? Or anyone need a hint?
I gotta try it first and see if it works.
Yep. Great.
Okay. Sorry. So just a small thing here. If I would want to mark some space for the mark model on the color on the how could I put the size in there? Great question. Yeah.
Sorry. Totally zoned out. My brain's off. Here, wait.
Yeah. My brain's kind of stuck there.
Yeah, right.
Yeah.
Alright.
If I have the cars,
Ooh, this is cool. I thought your computer was like off.
that's
I like the, yeah.
Oh,
You don't like sit next to you.
oh, sorry. I got this. No,
No, you're good. Yeah.
yeah.
Okay.
I know my computer have this. No sneaky thing.
Okay.
Yeah, if I have all those kind of mark model color, and I want to give some space in it, and I just go on to give my title.
Yeah. So
How can I put that in? Because
so
this
Malik,
is it.
right. So
Yeah, it's different.
yeah. So in the packet, you should be able to see the Malik
Yeah, like here,
syntax. Yeah, exactly.
like this one, but this is it.
Right, so that's-
I would on the size of the whatever the characters.
Right. So pull up your code again for me.
Yeah.
So here, I think you would do
what I need to do something
like
up there.
Let's see. So what are you trying to do here? So you're trying to allocate memory for each instance?
Yes.
Yes, okay.
I need
yeah.
to give
So
I need to give allocate memories when I'm typing my information in.
right. So I think you would do cars. So I think here you would just do cars.
Log the size of car.
Yeah, so like cars equals malloc n or I times size of. No, yeah, no. So cars equals malloc size of car.
So I don't need to do them separate.
Correct, because you're allocating something that is the size of the car struct.
Yeah, so I just need to do cars I.
So not cars I, it'll just be cars. Or yeah, because you're allocating the init. I don't think you need a.
Oh no, I mean my loop.
Right.
I mean my for loop. So I need I. So I do that outside. I think I have this one, cars.
Yeah, so that's going to be your array, and each instance of the array is going to be a car.
Yes.
It's going to be the size of a car.
Yeah.
So if you have 4, if n is 4.
If n is whatever it is, whatever
right.
I typed in, but.
Yeah, so now that you've done
some,
that.
Yeah, I also need when I insert the specific information like this.
So by doing
this,
is
I like you have the buffer says.
Let's see. So that's assigning each instance of the car's array to what is in the buffer, right? So because you've allocated the memory for the
cars already,
right? You don't need to reallocate.
I don't need to eradicate.
Correct. Yeah. Okay. Now you just need to assign it.
So I just
Does that make sense?
Yeah, I just scan F.
Yeah, that looks right.
Let me find this first.
Yeah, run it, see if it works.
Yeah.
Leave the space now. Eat only what you want to.
Oops.
Is it working?
No, I still need something. Okay, girl.
No peek.
Enter number of cars 5 is equal to car 1.
I need
So the make is So make is the problem.
Yeah, so it's
So-
still gonna be straight copy.
Right,
Right,
so
I need a Mylock some space.
Copies one straight.
no, because remember, you've already allocated space
Here.
for
You might.
a total of, oh, sorry,
Yeah.
for a total of 5 cars.
Depends on how
Right,
you
and each
declare your time
car contains,
So I scan.
so a segfault, yes,
Oh,
so
which
so
means
it
I
looks
didn't
like,
sign this.
correct, yeah, so I think, right, 'cause
That's
it
fine.
fails at make, is that right? Can you bring up the console again for me? Yeah, it fails at make. So where is your car struct? Char model.
That's from a comparison, comparison or something.
Yeah, because we haven't got this comparison yet.
Yeah, I got this problem before, so I just really Mylock each of these kind of cars.
You shouldn't have to.
Because I have to,
But I
I
thought it's
literally have to
55.
leave at 8:30 because of an obligation, another meeting. I'm just showing you the comparison function for now, just to help a little bit. If your comparison function doesn't look like that, you're probably in trouble. And the thing I handed face down is a complete solution, so you can like continue to work on it on your own if you have time. Anyone have something where you're getting sick calls? Huh?
I was getting some for numbers recently.
So, not to spoil your, you don't have to just, you can just sort of glance at this and then still do it. You notice that in the type, these are pointers, right? There's no storage allocated to these guys. They're not arrays like make of 50 or something. They're just raw naked pointers. This means that when you're reading these things in, you have to grab space for them. So see what's happening, the strings, you see what's happening here for the make and the model and so forth. You have to allocate space. If you try to just string copy into those, it's gonna segfault.
Okay.
Yeah, I think so.
Yeah, maybe I can do it. It's not Mylock this day.
Right.
Yeah, because I need to hard.
Yeah, I think that's where
Yeah,
the,
for but you might do this stable, give some space, because I know tomorrow I want to have a different part of that.
right. Yeah, sorry, couldn't help more. Yeah, but do you have a better understanding of it though, with the solution in hand? Okay, awesome. That's the goal.
Yeah, that's the goal. Yeah. Okay, it's not that I just the code a little bit different.
So this is a really abrupt, it's an abrupt ending, sorry, but yeah, well, I've been ordered to come somewhere.
Get out
Yeah,
of.
just like that,
Alright.
quick question, because I'm not
Yeah.
really getting used to what you are here. I know we have this homework, but I don't know if it's, oh, sorry. I'm not really getting used to you had this part, what I usually do is remark each of these and give them some space. I'm scanning it up. But currently I put some stable numbers here. If I just run this one to be whatever I have in, what should I put in?
Yeah, that's what I'm doing. That's what I'm doing here. So that it's mallocing on a case by case basis.
Yeah.
So I just read it using a big buffer.
Oh, just the.
Then look at the length of the buffer and malloc exactly the right amount.
Oh, okay, got it.
Yeah.
So-
And the big buffer is like a big one. Yeah.
Oh, yeah, so it doesn't. I just without finding the
Yes.
number, I
Yeah,
just
that's-
some
that's-
stable
that's
number,
right.
the program is working, but
Yeah.
I know it's some problems.
Thank you.
Yeah.
Jesus.
It was fun. If we probably needed 8 hours, but
Yes, thank you very much, Dr. Gold.
yeah, it was fun.
Thank you. Alright, so thank you all for coming. We really appreciate it. This one definitely had a smaller turnout than last week, but I think it still went pretty well. Did y'all like this, like smaller, more closer to one-on-one?
And you have a lot of stuff to type in.
Yeah, lots of things to type in. Yeah, thank you, Dr. Golden.
Yep.
And then, remember we have the Cyber in Cybersecurity talk tomorrow morning at 11 a.m. in PFT 1100. Hang out afterwards for some really good food. We're gonna get like La Madeleine's or Bistro Byron's or something. It's gonna be a bunch of fun.
Where is it?
It's in PFT 1100. Yes, tomorrow morning at 11 a.m. The speaker is Dr. Ashley Podporodsky. What a name, right? She's gonna talk about her initiative Cyber. She's a co-founder and just about her like contribution to women in the field of cybersecurity. She's super cool and super nice. She's friends with one of our professors, Dr. Bagili. But yeah, y'all should come hang out. If nothing else, get more free food. If you're not full of pizza already.
Yeah, and feel free to take any of the leftover pizza boxes or any extra cookies.
Yes, we have lots of leftovers. Yeah, right. I'm gonna end the recording.